Let's talk about hinge loss. Hinge loss is an important concept in machine learning, especially in classification problems and support vector machines or SVMs. It is primarily used to measure how well a model's predictions align with true labels, particularly in binary classification tasks. Hinge loss encourages the model to have a large margin between different classes. If data is not linearly separable, we have to use kernel tricks that allow us to map the data into a higher dimensional space. The higher dimensional space often transforms non-linearly separable data into linearly separable data. The multiclass hinge loss combined with the kernel trick allows SVMs to classify non-linearly separable multiclass data effectively. These are the sum of the key elements: hyperplane, decision boundary, margin boundary, true label, hinge loss formula, and calculation of hinge loss. Understanding the concept of a hyperplane is essential to understand or grasp how hinge loss works. In n-dimensional space, a hyperplane is n-1 dimensional subspace. Therefore, in 3D space, a hyperplane is 2D or a plane. In 2D space, a hyperplane is 1D or a line. The mathematical definition of a hyperplane is given by a linear equation. It is a1x1 plus a2x2 up to anxn equals b. Here, x is the feature vector and a is the weight vector. They have same dimensions. And b is the bias term. In 3D, equation of a hyperplane is given by this equation, which is a1x plus a2y plus a3z equals b. This is a plane. And in 2D, it is a1x plus a2y equals b. Again, it is y equals mx plus c. That is the typical equation of a line. And in 1D, a hyperplane is a point. It divides the 1D space or a line into two regions, one to the right and one to the left. Here we have 2D space and there are two types of data points, positive and negative. So we need to classify them. So this is the hyperplane. So it divides these two types of objects or data points into two separate classes. What is the optimal hyperplane? Here we have three diagrams. There are two types of data points. One is in red and the other one is in green. In order to classify them, we need a hyperplane. In the first diagram, the hyperplane marked in blue line does not correctly separate them. One red point is misclassified. Same thing in the second diagram. One green point is misclassified. But in the third diagram, we have perfectly classified all points. Even though two yellow lines classify them correctly, one of them is closer to green points and the other one is closer to red point. Hence, we can say the best or the optimal hyperplane is the blue line. It maximizes the margin, not closer to any class, and positioned at the center of the widest possible gap between two classes. Now we can label this blue line as the hyperplane or the decision boundary and these two yellow lines as margin boundaries. A hyperplane is a linear classifier as it defines a linear decision boundary in the feature space. Let's look at the criteria for classification. Here weight vector is theta, input feature vector is x, and the bias term or the intercept is theta naught. For binary classification, the true label is -1 or +1. And we can get the dot product between these two vectors, theta dot x. Then we can compute this expression, theta dot x plus theta naught. When you multiply this expression by y, and if it is greater than 0, then the classification or the prediction is correct. Otherwise, the classification or the prediction is incorrect. So these are the two vectors, theta and x. This is the bias term. Then we can compute theta dot x, and you can add this theta naught, the bias term, and you will get 4. If y is +1, then y times this expression equals 4. Then we can say the prediction is correct. If y is -1, then this becomes -4, which is less than 0. Then the prediction is incorrect. On the decision boundary, this expression is 0. On the positive margin boundary, it is 1. And on the negative margin boundary, it is -1. There are some limitations of using hyperplanes, and they cannot perfectly classify data due to these challenges like nonlinear separability, noise or outliers, or class overlap. The perpendicular distance from a point x1, y1 to a line ax plus by plus c equals 0 is given by this equation. Here d equals the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. Using the same formula, we can write the distance d here as d equals the absolute value of theta dot x plus theta naught divided by the norm of theta. On the margin boundary, whether it is positive margin or the negative margin, this absolute value becomes 1. Therefore, the d value here, this distance, becomes 1 over norm theta. In linear classification, the hyperplane and the decision boundary are the same. The weight vector theta is perpendicular to the hyperplane, and it points into the positive direction of the hyperplane. All these three lines are parallel because no data point can satisfy all three equations at once. As norm of theta decreases, the margin boundaries widen. A widened margin ensures that the decision boundary is not overly sensitive to small changes in points close to the boundary, and it keeps the boundary robust and helps generalize better to unseen data. Now our goal is to maximize the distance d, which is 1 over norm theta, that is equivalent to minimizing norm of theta, which is also equivalent to minimizing 1/2 times norm of theta squared. Now here we have 1/2 in front of this term because when we need to get the derivative of this term, the derivative does not need the constant 1/2 out front. This is the standard objective function for support vector machines. It balances the average hinge loss and regularization. Here, lambda is the regularization parameter which is greater than or equals 0. Large lambda means large margin. Optimal values of theta and theta naught will minimize the objective function. Now we need to focus on hinge loss, which is given by this expression. We use this expression to compute hinge loss. True class label is y, which is -1 or +1. X is the input and theta is the weight vector. Then f of x is the output. This is the model output. Now we can rewrite our hinge loss as max of 0 or 1 minus y times f of x. Here f of x is the predicted label. If this f is greater than 0, the model predicts the positive class. Otherwise, it predicts the negative class. Y times f of x greater than 0 means the prediction is correct. If it is less than 0, the prediction is incorrect. Let C be y times this expression, which is y times f of x. Then again we can write this Hinge loss equation as this. And if this agreement, here this agreement C is greater than or equals 1, then our loss is 0. Otherwise, loss is 1 minus C. So let's look at some examples. If this agreement C is 1, then loss is 0 because it satisfies this condition. Again, if it is 2, then again loss is 0 because it is greater than 1. If it is 0, then we have to follow this rule. This is 1 minus C, which gives 1. If C is 0.6, again less than 1, again follow the same rule and it gives 0.4. If it is negative 10, again using this rule, this becomes, Hinge loss becomes 11. Here we have 10 data points. Some of them have positive labels, the others have negative labels. This is the positive region and this is the negative region. So on this decision boundary, f of x equals 0, it is positive 1 here and negative 1 here. In this region, in this positive region, f of x is greater than 1 and here it is less than negative 1. So z equals y times f of x. If c is greater than 1 or equals 1, Hinge loss is 0. Otherwise, Hinge loss is 1 minus z. So this c value we can compute using y times f of x. For the first one, this label is negative 1 and it is on the decision boundary. So f of x is 0. Then c1 becomes 0, which is less than 1. Therefore, Hinge loss is 1 minus 0, which is 1. Again, for the second data point, y value is negative 1, f of x is negative 1. Again, we can have 1 here for c, and Hinge loss is 0 because it is on the correct margin boundary, negative particle on the negative boundary. And from here to here, this Hinge loss changes from 1 to 0. Therefore, we can assume Hinge loss for this third one should be something in between 0 and 1. So this is what we can say. This Hinge loss is greater than 0, less than 1. Since we don't know the exact value of fx here, we cannot compute the exact Hinge loss. For the fourth one, positive label and positive margin. Then we get again 1 times 1, which is 1. Then Hinge loss becomes 0. Then 5 and 6. These two data points, they are in the wrong region. The fifth one in this region and sixth one, it is in this region. It is not valid because positive particles or data points should be here, negative points should be here. Since they are on their incorrect boundaries, we expect a huge Hinge loss. So it is for 5, label is negative 1, f of x is 1. This gives negative 1, which is less than 1. Then Hinge loss becomes 1 minus minus 1, which is 2. Same thing for the sixth one. Now 7 and 8. 7 and 8, they are in the correct region. So this is the positive particle and in the positive region. This is a negative particle in the negative region. Therefore, we should expect the zero hinge loss. Here we can compute y7 is 1, f of x for 7 is something greater than 1. We said here in this area f of x must be greater than 1. Therefore, we know this number is greater than 1. Then according to this, hinge loss is 0. Same thing here. So this is negative 1 label, and this f of x should be very much less than negative 1. Then we get something less than negative 1. Then we get C as 1, greater than 1, something greater than 1. Then hinge loss is 0. And 9th and 10th particles, data points. So they are in the wrong region, invalid region. So 9 should be somewhere here, but it has crossed all these 3 lines in the invalid region. Similarly, 10 is in the invalid region. Therefore, we expect a huge hinge loss. So again, for the 9th one, label is negative 1. Here it is very much greater than 1 for that fx value. Therefore, this is very much less than 1. Very negative value here. Then hinge loss is 1 minus a large negative value which is greater than 2. Here the same. It is again greater than 2. We can say it is greater than 2 because since this 5 has a loss of 2. Again 6 has a loss of 2. So then 10 must have something greater than 2. Similarly 9 must have something greater than 2. Therefore, they incur huge hinge loss. Now we can summarize our results. There are 3 categories. If y times f of x is greater than 1, then the data point is outside the margin and no contribution to hinge loss. If it is 1, then the point is on the margin and no contribution to hinge loss. Again, if it is less than 1, then the point violates the margin constraint and it contributes to hinge loss. Now we can summarize our results. This is the positive region, this is the negative region. F of x equals 1 on the positive margin, it is 0 on the decision boundary and negative 1 on the negative margin. And if we assume C is the midpoint between B and D, then at C, f of x is 0.5. Similarly, if E is the midpoint between D and F, then f of x at E is negative 0.5. Here we know in this area f of x is very negative. Then let's assume at G f of x is negative 2. Now this data point which has a label positive 1 is moving from A to G, that is from valid region to invalid region. Now hinge loss is at A is 0, B is 0 because this is still a valid region for this data point. At C it becomes 1 minus 0.5. Here we have used this equation y times f of x. Since y is 1, this is just f of x. Now at D, hinge loss is 1 minus 0. It is 1. We always know the hinge loss on the decision boundary is 1. Again at E, it is 1 minus 0.5. This is 1.5. At F, it becomes 2 because this particle or data point is on the wrong boundary, or the opposite boundary. Therefore, always this has hinge loss 2. At G, it becomes 1 minus negative 2, that is 3. Now we can see all these values are non-negative. Therefore, we can say this max function ensures the result is either 0 or positive. Therefore, larger hinge loss implies larger misclassification it also implies the data point is far away from the correct class. Finally, we can say hinge loss increases linearly for misclassified points as they move further from the correct classification region.